In this video, we'll look at the second part of the Fundamental Theorem of Calculus. This part has another interesting consequence, and the statement here is the following. Let f be a continuous function on AB. Really, I only care that it's integrable, but that's okay. Then what happens? Then the definite integral from a to b of f of x dx can be computed as f of b minus f of a for capital F any antiderivative of little f, i.e. this big F is an indefinite integral of little f. What does this do for us? Well, on the whole, this is fantastic. This means we no longer need limits and Riemann sums to compute definite integrals. This is sort of analogous to our shortcut rules for derivatives back in our derivatives chapter, but the idea is now I can just use antiderivatives to help me compute these definite integrals and don't need to resort to rectangles and limits and all that stuff. The same goes for things like areas under curves. Those are definite integrals, so now I can find them using these antiderivatives directly, as opposed to having to use rectangles and limits and all that stuff again. One point about this, it does say any antiderivative. And that's because the c doesn't really matter, right? If I have an f of x being some antiderivative, any other one is just f of x plus c. But if I'm doing f of b plus c minus f of a plus c, the c's are just going to cancel. And so it doesn't matter which one of these plus c things I use, I'll get the same thing as f of b minus f of a. At the end anyway, it doesn't really matter. As an example, let's find the area under the curve y equals square root of x between 0 and 4. This is something that would have been nearly impossible, if not impossible to do with our Riemann sum stuff before, because we had no power formula for square root of x. So we're grateful here we can now use indefinite integrals instead. So the area under this curve should be the definite integral from 0 up to 4 of square root of x dx, which now I can compute as f of 4 minus f of 0 for any antiderivative of square root of x. So what's the antiderivative? Well, the indefinite integral of square root of x, this is x to the 1/2, should be x to the 3/2 over 3/2, which is 2/3 x to the 3/2 plus c. But because I'm going to subtract anyway, I can sort of forget the plus c even exists and just do it directly. So what do I get? Well, then I get that my definite integral from 0 to 4 root x dx should be 2/3 times 4 to the 3/2 minus 2/3 times 0 to the 3/2. This is just 0. And so I'm left with 2/3. 4 to the 3/2 is 2 cubed is 8, which is 16 over 3. Now, a little argument as to why this is true. The main point is we know that if I take the function a of x to be the definite integral from a up to x of f of t dt, we know that a prime of x is little f from the first part of the Fundamental Theorem of Calculus. This means this a is an antiderivative for my function little f. Well, then what do we notice? Well, then we look at a of b minus a of little a. Well, this is clearly integral from a to b f of t dt minus integral from a to a f of t dt. But this is 0. So we then know that a of b minus a of a equals integral from a to b f of t dt, which is what I wanted to show in the first place. And the fact that it works for any antiderivative comes from the issue that I talked about previously. The fact that if I look at any other one, it has to be this plus a constant, and the constants will cancel out. That's the idea of the second part of the Fundamental Theorem of Calculus, this expression right here, the fact that I can now evaluate definite integrals by first finding antiderivative and plugging in values as opposed to going through Riemann sums. This is the best step we have for now computing these formulas, finding areas under curves and other things that involve integrals, because we now don't have to resort to Riemann sums, which is a big burden of trying to solve these problems directly before we had this theorem.